Hi all, this is Ramakrishnaya, working as ad hoc lecturer in Department of CSC in JNTU College of Engineering, Pulivendula. Today's our topic is red block trees as part of our subject advanced data structures. Why the red block trees? To make the tree as balanced. Balancing means it should give the logarithmic performance for all insertion, deletion and searching in worst case. The logarithmic performance means order of log n for all the operations. Another balancing tree is AVL tree, which we have discussed about it already. These two balanced trees are best suitable internal memory applications. Coming to the definition of red block trees, red block tree is a binary search tree with each node colored either red or black. In addition to this, the red block tree should satisfy the property of extended binary search tree property. Extended binary search tree property in the sense, in the binary search tree, the null pointer should be pointed to the external node like this. So external node should be represented as square like this. So in addition to the extended binary search tree property, it needs to satisfy some other properties. Here 3 are here. So the first property is the root in the red block tree should be black, and also all external nodes are also black. So the root is black and external nodes are all black. So the property 1 is satisfied. Coming to the second property, no root to external node path has two consecutive red nodes. So if you are considering one path from root to external node, in this path there should not be two consecutive red nodes. So this is one path and this is one path, it doesn't have any red consecutive nodes, and this is also one path, it doesn't have two red consecutive nodes. So this is also satisfying the property 2. Coming to the property 3, all root to external node paths have same number of black nodes. So this is root to external. So this path has one black node, and this is root and this is external. So this path has one black node. So this is also one more path, this has one black node. So all the paths should have same number of black nodes. So according to this property, this is the example of red block trees. So the previous discussion was coloring with the node. So coming to the coloring with the pointers, when you want to assign a coloring to the pointers, the definition should be like this. So the pointer from parent to the black child is black pointer, and pointer from parent to the red child is red pointer. In addition to this property, it needs to satisfy 3 more properties. So the first property is pointers from internal node to the external nodes are all black. So pointers from internal nodes to external nodes. So this is the internal node and this is the external node, and from this internal node to the external node it is black. So it is satisfying. Black means thick line is representing black, thin line is representing red. So here we are representing with the black, it is satisfying the property 1. Coming to the second property, RB2, so that is red block tree 2 property, no root to external node path has two consecutive red pointers. So here in the entire tree, it doesn't have any two thin lines, consecutive thin lines. So this is thin line followed by thick line, followed by thin line, followed by thick line. So here no root to external node path. From root to external node, it should not have any two consecutive red pointers, means thin lines. So this is all, this entire tree is satisfying the property 2 also. Coming to the third property, all root to external node paths have the same number of black pointers. So this is the one path from root to the external node. This is one more path from root to external node. So this path has, this is one block pointer, this is one block pointer, means this entire path has two number of block pointers. This is one more path, this is one block pointer, this is one block pointer, this entire path has two number of block pointers. So what is, all root to external node has two same number of block pointers. Same number of block pointers in the sense this is 2, this is 2. So this is also satisfying property 3 also. So coming to the rank of the node, when you want to calculate the rank of the node at a particular node, so the rank of the node in the red block tree is number of block pointers on any path from the node to the external node in its subtree. So coming to the same figure, so if you want to calculate the rank of 50, so here if you want to calculate the rank of 50, so from here, from this node to the external node, how many number of, from this node to the external node, how many number of block pointers are there? So here this is one block pointer, one block pointer. This is also external node. In this path also it has 2 block pointers. In this path also it has 2 block pointers. So the rank of this 50 will become 2. Why? Because number of block pointers from this node to the external node. So according to this point, the rank of the external node will become 0 always. So in the same figure, we will prove one lemma. According to the definition of red block tree, we will prove one lemma, one condition, that is length of P less than or equal to 2 into length of Q. So let us consider P and Q are two external paths. So let us consider this is one path 65 to 5 in this way. 65, 50, 10, 5 to external node is one path. 65, 80 to external node is one more path. Here the length of this path is 4. The length of this path is 4 and length of this path is 2. So here this is a P, this is a 2. It is satisfying the condition P less than or equal to 2 into length of 4. Means so red block tree will satisfy this type of lemma. So length will become number of pointers on the path. So representation of red block trees. How we need to represent a red block tree in programming. So here we need to implement null pointers in the binary search tree to the external pointers, first thing. And coming to the colors of pointers, how we will assign the colors to the pointers and nodes. Here each node needs to store one additional bit to store coloring. So each node should have one additional bit to store coloring, and or so if it wants to store the coloring of its pointers, it needs 2 more additional bits. So in the same figure, so 65 is a node. If it wants to store its color, it needs one extra bit. If it wants to store its pointers, it needs 2 bits. So to store this color, it needs one extra bit. If it wants to store this color, it needs one more extra bit. So here storing of coloring and storing of its pointers color, both are same. So both are same almost. In our discussion of the insertion and deletions, we will state the node colors but not pointer colors. Why? Because so pointer coloring will needs to store 2 bits. Of course the same it has only same space. In this pointer color changes may be inferred. So in our further discussions, pointer colors will may be inferred but not as part of our discussion. So searching, coming to the operations of red block trees, the first operation is searching operation. So the searching operation, this follows the algorithm which was used to search an ordinary binary search tree. So the same algorithm will be used here. So the red block tree mechanism, red block tree balanced tree will give the worst case time complexity for RB tree is order of log n, for binary search tree of its order of h. N stands for number of internal nodes in this thing. So the searching of red block tree is same as ordinary binary search tree.